Write all the word problems down.
No, I'll take them out of the book. That way you don't have to write them all down. You just refer back to the book. But there's a few other things. 3-5. Mostly exponential. Applications of exponentials, mostly. For this part. The exponential ones are based on two curves. Two different graphs. Two different pictures. Curves. They're called curves. Curve number 1 is this graph. Comes along the negative x-axis, hits this point here, and shoots up. What would the general equation of this thing look like? 2 to the x would be one possibility. The one we're going to work with is, I'll write e to the x for now. We'll change it in a second. The other possibility is the backwards one, coming down. This one would have a graph of what type of equation?
A log.
No, it's not a log.
Sorry.
It's still hugging the x-axis.
2 to the negative x.
2 to the negative x or e to the negative x. One of those two. All right. Now, for word problem possibilities, you could only worry about the positive x-axis. So the only part of the graph we're going to be working with is the intercept and the point after it to the right. So when we talk about applications, we start at the x equals 0 or the y-axis and we move to the right. So this one over here is going this direction. And I think I gave you these words before.
Say that again.
We only work when x is positive. Actually, t. This is going to become the t-axis, time, seconds, minutes, hours. You can't have negative time because Einstein says you can't go in the past. No, there's no obvious about it. Don't even talk.
Yeah.
So this one here, if this is the t-axis, as time goes on, something is actually growing, and we call this so what grows exponentially?
A tree. 2 to the x.
I guess a tree. Maybe, maybe not. No, I mean as in a quantity in the world, something realistic.
Oh, money. My
Money.
height.
Okay, money. What else?
My height.
Your height. It's zeroed out.
You're not growing.
You're at a constant level
Dude,
there.
You're
not
growing
measuring.
anymore.
She wasn't measuring.
You're
Now, as you grow up, you don't actually follow exponentially. You grow on a logarithm scale.
Okay.
I'm just saying. Population, bacteria growth, money, of course, heart rate. Those are the general ones that we're going to work with here. Population, money, and cell division type growth.
Doesn't always have exponential growth.
What doesn't?
Money.
If you put it into an interest rate, compounded monthly with a constant interest rate,
Oh,
it's
so we're
always
talking about interest money.
yeah, interest
Okay.
money, not value of money.
Okay, I'm like, okay, if we
That's
were
what
doing
they are.
value of money and it went down, would you be able to use the other one,
We'll cut
the
the
e to
door.
the negative x or whatever?
The
for
value of money
inflation?
does go down.
In inflation and
Yeah.
everything?
Something like that.
Okay.
What? This year you're
That was her boyfriend.
What?
going. This one, of course, is called
Say them first.
Second, we closed the door. I said I was meant to.
Oh.
I said it was a
Okay, then.
exponential decay. Now, what decays?
Inflation is money.
Money. The value of money does decay. How much you can buy with $10 today is totally different than what you could have bought with $10
Old people's height.
20 years old.
That's
That is so
I don't
bad.
think growth would be a lot, because when you get old, you shrink.
All right, what else decays?
Bone.
What's that? Fossils? What do you mean fossils?
Like carbon dating.
Carbon dating. So over here you have, carbon dating,
Hold up.
isotope delay, decay, isotope decay. This is population, money, and money with interest.
I'm just going to put interest.
interest, and cell division. What else besides isotope decay?
Radioactive.
Radioactive.
Oh, okay.
Now, carbon dating is actually radioactive decay because carbon-14 is an unstable isotope and it decays just like radioactive materials.
Isn't it just like carbon dating is only for carbon nanotubes and radioactive?
Only for living things have carbon-14.
And so radioactive decay is for everything else?
Radioactive decay is just for radioactive isotopes. Can't be for everything else.
You know what I mean?
I know what you mean.
I
So-
don't know what you mean.
Both of these situations fall under this formula. How do I want to write it though? We'll say A equals P sub 0 e to the kt. I always learned it this way. If you're talking about money, that one makes more sense. A equals PERT.
What?
A equals
What's
PERT. They're exactly the same formula. It's just here you have R for rate, and here K is what's called a constant.
Why is it K instead?
Where did the little...
What's the sub-zero mean? Anybody know?
It means
It's a temperature.
The beginning. This is an initial population. Where over here, this is just principal, if you want to think of it that way. What's that? Oh. So when you see things like P sub 0, T sub 0, S sub 0, you're going to see a bunch of that if you ever get to calculus. Every time you write something like that, it just means initial. What you started with. What you started with. All right, so this formula is the one we're going to concentrate on. If you want to memorize it, this is easier, and it works exactly the same way, so there's no difference between the two of them. So for example, let's do a population growth. In 2000, Rocky Mount had a population of 123,000.
I feel bad for them.
In 2012, Rocky Mount had a population of 112,000.
There was a lot of murders that year.
There was a lot of murders that year.
Yeah, I remember last year.
We won't get into that.
It was covered in.
It is possible for populations to decrease.
Yes.
Even horribly so, like Easter Island. You know, they had people one time and they didn't the
Didn't they
next.
just like chop down all the trees?
Yes,
and
I-
use all their resources up.
Yeah.
Silly things.
It's like Laura.
They all
Wait,
died
what?
because they used up
That's
their
right.
resources.
Great. Is on
Oh,
trees.
yeah, that is true.
Ponies.
Ponies, but it was snowing. It was so pretty.
Ponies?
You're not talking about the commercial
I think
where
they're outside,
girls
like-
get Pony.
Yeah, outside. Outside.
Bunnies.
All right.
Hold on.
In 2000, Rocky Mount had 123,000 people. In 2012, they had 112,000 people. And according to this information, we should be able to guess how many they have in 2050. All right. Now, have you ever done varies directly, varies inversely type problems?
Maybe.
When you do a varies directly, varies inversely problem, it has two parts.
Hold on.
Part 1 and Part 2. These problems also have Part 1 and Part 2 parts to it. The first part is find constant. In this case, it's K. Part 2 is answer the question. And you have to be really careful when you read these not to mix the information from Part 1 and put it into Part 2 or vice versa. So when I read this, I have to be able to distinguish what's Part 1 and what's Part 2. So what's going to give me Part 1?
Doing the slope.
I don't do slope. There's no, well, you can't talk about slope, it's a curved line. We need the K, so what piece of information is going to allow me to solve for K?
Poet.
Both of these,
Yeah.
the top two. So I need those two to get to K. Now that's not going to do me any good for the 50 years after, it's actually, 50 years after 2000. But once I have K, it actually becomes kind of an easy problem. So, plug in both. Plug in your information into the formula, so you go A equals P0 e to the kt. A is the total amount of the population after a period of time. So we can actually call this A of t as a function. P sub 0 is initial population, and E is just, the function. And so what goes in for A?
112.
112. That's how much happened after a period of time. So this side gets 112. I'll keep my answer in thousands, so I'll just drop those 3 zeros. But when we get to the end, it'll have the same solution. Equals, what's the initial population?
123.
123. E to the, I don't know K, that's what I'm looking for, but time is 12 years. So all we need to do is to solve for K. What would you do first? Alright, pause.
Where do you, why is the A 112?
A is what the population is going to be after a period of time. We started in 2000. After a period of time of 12 years, we ended up with 112,000. So that has to be A. Even though it's a smaller number, it's what happened after time passed. And the initial population is the one we're starting at, which is at 2000. So the initial has to go in that other slide. 1, 2, 3. P sub 0.
Would you split up the first thing you do? Would you split up like 123 and E and make it ln?
Well, eventually, but I gotta get that 123 out of there.
You do?
It would be ln 123 plus.
I need to get it out of there completely.
Then divide about 123.
Yeah, divide both sides by 123. Just get it out of the way.
0.91057.
4 decimal places, what is that?
0.1906.
It's like a bunch of decimal places. So
Just do 4.
0.9106.
0.9106.
I would just leave it as a fraction until at the very end.
You can. That'll give you a better answer.
Yeah, that's what.
Yeah, you can get a better answer out of it. Then this side is e to the, you can
So we
switch
should
it
leave it
around.
as a fraction first?
12k. You could leave it as a fraction if you want an exact answer. If you're worried about being off a little bit. It shouldn't throw us off too much.
Okay.
12 out in front.
Well, you have to do something else first.
Right. You have to change it to ln.
Yeah, ln both sides. So ln this side, and you ln this side. What happens when the ln and e run into each other?
They cancel out.
They go poof. Don't say the word cancel
I'm
because that
sorry.
implies inverse identity. Poof. So this side is ln of 0.9106 is equal to, well, 12k and k12. It really doesn't matter which order you treat it in. Now remember, this is just solving for k. We're not even getting to solving for what the question is asking. So after you divide both sides by 12, you're going to get k approximately. Here you need a decimal.
0.075.
It has to be negative.
Negative 0.0078.
Negative.
I got negative 0.46.
Oh, now I'm worried. Where's my calculator? You have a calculator?
Yeah.
No.
So let's see here. ln of 0.9106 divided by 12. Negative 0.0078.
ln.
0,
Are you doing 112 over 123?
Yeah.
That's why you're getting a different answer.
7, 8. Make sure you close that parentheses. The one after the 6.
Would she be getting a different answer because she's doing 112 over 123? Because that's what she's
Just a
doing.
slightly different answer, not a horribly different answer.
I got it back.
112 divided by 1.
Oh, it's because I divided by 2 instead of by 1.
Oh. Yeah, it actually gives you the exact same answer to 4 decimal places.
If we use, instead of like slumming it down to 112 and 123, if we use 112,000,
The zeros would cancel.
yeah, zeros.
Because you have thousands and thousands, so the thousands just go away. Yeah,
Are we just
it's
doing
always
it
going
up
to
to
come out
3
nice.
decimal points?
What's that?
Are we doing it up to 3?
I do 4.
Okay.
I do 4. Gives you better answers.
Excuse me.
All right, so that's part 1. Over here, this is part 1. You solve for the constant. In this case, it's called the decay constant because we're going downhill. Then you set up your equation again. You go a equals p sub 0 e to the kt. Plug in what you know. Now for the second part, do I know the final population? No. Because we're looking for after 50 years, and there's nothing about how many people are in Rocky Mountain after 50 years. So leave that alone, that's A. Do I know the initial population?
Yes.
Yes.
123.
123 will drop the zeros. Because we'll just say our answers is in the thousands. In the thousands. E to the K. Do I know K?
Yes.
Yeah, we just found it down there. Now that K is never going to change for this problem. So if they ask you for a different year, that K stays the same. And then T is going to be 50. So we're solving for this. You type it in here.
I got
handy dandy calculator.
83.2779.
Now make sure you read it in the right frame.
I'm sorry, 83,000.
Yeah, times
277.
83,270.
What'd you get?
Wait, what?
I didn't.
I didn't get that.
83,277-ish.
I got 83,248.
I didn't get the dude.
What did you use
Did
for
you put
K?
like
Okay, I put
negatives
the
and everything in the
entire decimal for okay.
The whole decimal.
Yeah.
Well, once
Don't
you do
do
that,
that.
it's going to be different than my 4 decimals.
Well,
That's fine.
when
You should be really close to 83,000.
83,248.
You're close. You're off by a few people. It's not a big deal. 61.
What?
Okay.
Hey, I got 61 something too.
Yep.
Now I'll find out.
Yeah, we
I'm wondering.
really went down.
Don't put parentheses there.
Alright.
Because what you're doing is you're doing this. And you're taking that answer times it.
123
Once
E.
it puts a parenthesis there,
All that.
this time, that's done.
Close it.
Don't separate the. Don't put extra parentheses in between the numbers.
Well, that's what made me do it by
Don't over parenthesize it.
Yeah, Harry Potter.
Let me try.
Harry Potter. Hermione doesn't even end up with Harry. She's in front.
Yeah, that's what it was. Can't do it.
Let's talk about Harry Potter now, Craig.
And
They won't
Harry's
let you do it
You
unless
never
you have the
leave
time.
all
Can't do 2 separate parentheses. So, yeah.
compared to how Neville was at the beginning. Compared to how Neville was at the beginning.
Not the game. Half-Life. Throwing things around. Half-Life is interesting. If you start off with 100 kilograms of uranium-238. I forget what the half-life is. I can look it up. I think it's like 700 years or something silly like that. Let's make it shorter. This is a radioactive isotope. So let's say the half-life is 20 years.
Can I just say something?
Yeah.
You're going to kill someone with 100 kilograms of uranium.
What about that? Yeah, well, just don't play with it. So let's say that a half-life of U-238 is 20 years. So after 20 years, how much of the stuff do you have left?
50.
50 kilograms. It doesn't like melt away or disappear, it just converts over into another material. Does anybody know what it converts to?
Like
U-238, what's it convert to?
It converts to the thing
you.
behind it.
Me too.
Nobody knows?
I used to know to half of
Lead.
lead.
Changes into lead. So every piece of lead that you can hold in your hand is actually slightly radioactive.
Cool.
Yeah, that's
Slightly.
why we.
Wait.
But uranium-238
This
converts into lead, which kind of
This
neat.
isn't like legit lead, is it? 'Cause
No, that's graphite.
yeah,
They don't do lead anymore.
Yeah.
No, that will kill you.
Lead paint.
After 40 years, how much of the material is going to be left?
25.
25 kilograms. It just cuts in half. So after 60 years,
12.5.
12.5. Now, if I keep on doing this,
6.25.
am I ever going to run out?
3.12.
Stop it. Am I ever going to run out of uranium?
No.
No, because if you cut it in half and half and half and
It'll
half,
keep going.
it never ever gets to where it's supposed to.
Zero.
Yeah, it never gets to zero. So one way of describing this formula, trying to think of the best way to do it. Every 20 years, so like 20x, where x is every 20 years. times what you start off with. That's one way of doing it. But what we're going to do to it
We'll do the A formula.
is we're going to describe it with this formula. A equals P0 KT.
Is that not?
1,000 years. Now this is going to be a percentage of the original material because what did I tell you?
How much there is?
How much we started with.
There's gonna be 50 halves.
So a lot of people get confused with this question because I don't tell you what we start with. So you start off with A equals P sub 0 e to the KT. How much am I starting with?
We don't know.
According to the formula.
Half.
No.
One.
What am I starting
One.
with?
1.
Okay.
0.
According to this formula, how much am I starting with?
100%.
Stop it. According to this formula, how much am I starting with?
P.
P sub
0.
0. So choose that as your starting point. What does A become then? 1/2 P sub 0. So you get a half P sub 0 over here
What?
and a P sub 0 over there. If you start with 100 kilograms, you end up with half of it, which is 50. So that becomes a half-life. E to the K, now what's T in this case?
20.
20 years. After 20 years, P sub 0 is going to become half of itself. So far, so good. And what's really neat about this is now when you start solving for K, what happens to the P sub 0s? They cancel. So it doesn't matter how much you start with, it just matters that it's being cut in half. So this becomes a half equals e to the 20k, and then start solving. What do you do to both sides? ln it. So you're going to get ln of a half, or 0.5 if you want to write it that way, is equal to 20k. Remember when ln and e run into each other, they go poof. And you solve for k, and you get k equals ln of a half divided by 20.
Negative 0.0346.
Negative 0.0346. At least 4 decimal places. Unless you're one of those perfectionists that use every single decimal that they see on their calculator.
Ooh. Damn. Harry Potter.
Harry Potter. Set it up again.
Hold on.
Hold up.
You just wait 1 second.
Wait, so is this K?
That is part 2.
This is part 2. I always separate mine with a little line, even when I do my own work, just to keep my brain straight. One half of the problem, other half of the problem.
Right side of brain, left side of brain.
Now, we want to know how much is left after 1,000 years. So A is what we're looking for. P0 is still P0. And it becomes e to the negative 0.0346. And T in this case is
1,000.
1,000.
Wouldn't that be 1/2 piece?
P sub 0. We only use the half P because after 20 years, we're going to have half of the material left. That's the only reason we use that half over there. But when we come back to the original problem, we substitute in the K, we still have our initial population, and we're looking for a new amount. It's not going to be a half.
Negative 34.65.
Hold up.
And then calculator time.
We go with E.
Another E. So E.
8.8.
E. Where's
E to the negative 16.
A to the negative 0.0346 times 1,000, parentheses, equals. Woohoo!
It has a negative 16
Yeah.
power.
So this would be times 9.406 times 10 to the negative 16.
I got 8.8 times 10.
Did you use the whole decimal
Yes,
again?
I
I ain't told it to you.
I got 8.9. I got something.
If you put in the whole decimal, then yes, you're going to get something different. But this should be the answer, 9.406. Now, what's that negative 16 mean?
It means that you have to go that way 16
16
times.
decimal places to the left,
Alright, the little
which
dot-
makes this really, really small.
The little dot after the P. What we got going on there? That's the no,
That's
no.
sub-zero.
Okay, I thought.
Wait, so we just keep P sub 0?
Yeah. So this is a fractional portion of whatever you started with. So if this is 100 kilograms, you would times it by this, and basically you end up with barely anything. So after 1,000 years, this material is basically not an isotope anymore. There's just a tiny, tiny little fraction to it. How if we shrink up the years? Let's look at maybe 100 years. Now, let's make it weird. 75 years.
I thought you said we were shrinking the years.
We did. We went from 1,000 to 75.
That's
Just like that.
Just like that. So let's see what that does. It goes A equals P sub 0 e to the negative 0.0346 times
what? 75.
75.
What do you say?
I just made it up. I just wanted to see what portion. That one became way too small, so it's basically gone.
It's 0.0746. There's P to the Z.
0.0746. Now this one's a little more easy to understand. So you get A equals P sub 0 times, say it again? 0.0746.
46.
Now this is a percentage. How do you change that to a percent?
To the right 2.
To the right 2. This is 7.5% leftover. So after 75 years, you're only left with 7.5% of the isotope that you started with. Yes, Samantha?
I want to ever hit 1.
1.
I'm trying to make it hit 1.
1%.
Why?
If you want 1% out of this, you put P0 here, you put 0.1 P0 here. That's all for T.
I just put 0.5 in for the E sub 0 thing. I mean E to the power.
Sam, you're confusing me.
You're confusing me.
For the time, I'm putting years in, trying to see if it goes to 1.
Hold on. What? What?
Why would you do that?
Just to see if it could.
You're trying to get this to 1?
Yes.
Then you got to put a time at 0 in there. Because e to the 0 is equal to 1. What if you want to know specifically, like, I want 0.25, I want, let me put it over here, want, oh, I didn't spell it. Want 25% left.
Parents sounds like getting a tattoo.
Yeah, it does.
What's that?
Pen sounds like where you get a tattoo. A tattoo.
Oh, you hear
Yeah.
it too? That looks lovely.
Yeah.
Uh-huh.
I want it also.
So, if you want 25% of the material left, that would be 0.25 P0, P0, e to the negative 0.0346, T. In this equation, what are you solving for?
T.
T. So it basically sets up the same. You divide both sides by P0, you end up with 0.25, a quarter of what you started with. And then you can solve for T, and T, of course, is measured in
Time.
what kind of measurement though? Time?
Years.
Years, because it was 20 years as a half-life. So this would be e to negative 0.0346
40.
T. So what's T equal to?
40.
Approximately 40 years?
40.06.
40.06 years. That makes sense.
So,
2 half-lives.
if you just want to find what percent, like,
What percent you're looking for,
you just put it in front of.
Yeah.
P0. And then you just throw that in the A spot. So if I want 10%, put 1 P0. If I want 1%, 0.01 P sub 0. So forth and so on. And then just solve for T in that case. We're not solving for K.
Okay, hang on, I have a question.
Go for it.
You LN'd both sides, right? You
Both.
just.
L on both sides.
Yeah.
So it'd be L of 0.25 equals negative 0.0346 T. And then divide by the negative.
So we got your first answer on the right. Yeah, right there. So that would be the answer.
That would be the percentage. If we multiply that by 100, so that would be negative 14%. Which basically is
That is 6.
nothing. Yeah. It's
Yes.
basically nothing.
So that's how you would write it. Like,
Alright.
You could leave it like that too. This is how much is left as proportional.
Boring.
But this is more interesting. I'll leave it as a nice number.
yeah.
Yeah, that's easier to
So it'd be
understand.
7.5%.
7.5% left over of the original.
Logistics.
What else do I have in here? More boring
They
questions.
have the UPS machine.
That's the same. Ooh.
Do I have time?
Yeah, we got plenty of time. Logistic growth models. These are cool.
Check 'em.
Logistic
What time is it?
What can Brown do for you?
growth.
Okay.
Should call this a UPS growth model. Nobody gets it. What UPS is? Logistics. Guess not.
I don't know why I just
Just retreat over it.
What's the difference? Oh, I see.
Stop calling out yourself.
I'm sorry. This is considered a logistic growth model. Now, the problem with exponential growth models is if you have a population, eventually it's going to go off to infinity. It's going to get really, really large as time goes on. The neat thing about this model is it actually fits the real world just a little bit better. For instance, if I have f of t is equal to 150 over 1 plus, let's say 5e to the negative 0.02t. That's my function. I'm just making it up. Let's see what happens. When t is equal to, I don't want to go too far, 2. What is f of t equal to? F of 2 in other words. Let's record your calculator.
I don't know. I'm trying to prove here.
Trying to get used to your calculator here. Be really careful of that bottom. Put it in parentheses.
I got
34.
I got 25.8.
Hold up.
What's everybody doing differently now? Well, I did it differently because the last time I put 2 of them.
I got 25.84448.
Yeah, that's what I got. I'm waiting for everybody else to see if they get it.
I got 34.4.
Oh dear. That's not good.
I got 4.
Calculator work. I love it.
I did it piecemeal.
Wait, 4.3.
150 plus divided by.
Yeah, still have put parentheses on the bottom.
Yeah.
Whoops.
25.8444.
Shit.
Let me see your calculator.
I will do it one more time.
Harry Potter face.
Harry Potter. Not Harry Potter, it's Harry Potter.
Harry? Harriet Tubman.
25.8.
It's definitely.
Oh, I know that's Harry is 5.
25.85.
Getting to me, and I thought that said point.
She put like
It's
40
0.2.
parentheses in.
Yeah, it goes down. That's
She
probably
put like
fair.
40 parentheses
No, you're
in.
not.
Do t equals 10. In other words,
It's time for a 10.
f of 10. Let's see if you get it right this time.
Okay.
You saying it's time for a 10? Like a break?
T for 10.
Oh. Time for a 10-minute break at work?
Okay, I don't.
Don't say it out loud.
6.1. -8.
What?
Hold on,
20.
Sam, you done.
29.44.
Yeah, 8.4.
Are you using 0.2 again or 0.02?
No, I'm using 10.
Yeah, but
Negative 0.02
Oh, yeah,
negative
times
0.02
10. Oh, I
times
forgot.
10.
I got rid of 4.09.
know.
29.44.
I replaced the 0
Eight.
thing.
Maybe next time.
I'm telling you, okay.
I love calculators.
It doesn't work. It works
Strike
when
out.
I Okay. No, I know what I did.
Type in 150
No,
29.9.
divided by
It works when I.
parentheses
now.
Okay,
plus
I'm finding it.
caret
Please.
negative 0.02
There
times
has to be a
There's a
5 in
five.
front.
5 in front of the E. What? Why?
5.
Because it's.
There.
Oh.
Because it's 5 each.
Because it's there. All right, how about t equals 100?
Oh,
I'm not going to get this wrong.
Yes, you are.
somebody will.
89, huh?
Oh crap, no, I did it wrong. Sorry.
I still got 154.9. What the heck?
I didn't get it. I didn't get it wrong. What about
89.410. I want to.
89.46.
Yes, I'm happy.
They really sabotage your calculator. So
You forgot your parentheses in front of the 1.
I'm trying. I wish
got
our
it.
work would blur down. I'm trying over here.
What do you mean?
I'm trying to figure out
You
the
just-
answer. You guys blurred it out.
You told us not to do that.
No. You need this parentheses because you have a long fraction bar. It's parentheses here, parentheses there.
That's what I thought, but I mean.
No, when you put, where you guys were putting parentheses before was here. You were doing negative 0.02 parentheses,
get this
parentheses 10. And you can't do that because it separates the numbers.
I separated the line.
This is what, 89? How about t equals 500?
I won't say the answer.
Please don't.
I got the right answer for 100.
Alright, now try 500.
One, no.
I see I'm going to edit this tape to death. Delete.
I could have sworn it's all under R.
You stop learning that answer.
That's
right.
This one goes to?
1.9.9659.
Blah, 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 blah.
Oh my gosh, chill.
Put in 1,000.
Okay, I don't wanna.
I'm tired of this.
I know. I'm trying to get a point across though.
149. As you.
Oh my gosh, I'm so
It
smart.
won't go to 150.
It will not make it all the way to 150. This is
Because it can't equal 1.
149.96.
Yeah, so it would be one. Wow.
It gets closer and closer and closer, but it will never ever get above
150.
150.
Or 2 150. It won't equal 150.
No, it won't ever equal 150.
No, when I put in 500, I got 96.
You got what?
I got 149.96 for 500.
Yeah,
And 1,000?
I didn't do 1,000.
149.99.
0.99.
9999985.
So it's really close. This one's 96. Okay. So what's going on with this graph? Well, it's growing in the beginning, like especially between 10 and 100.
It's still growing.
It's
but not
growing.
as much.
But then the rate of growth decreases. It slows down.
Quiz time.
The, what?
Yep.
Culture too.
Yeah.
Give me 1 minute.
I can't.
The graph of
do
this.
it.
Hold on. The graph of this is kind of cool. It starts off looking like an exponential. This would be where you start the graph. It grows like an exponential for half of it.
And then it goes flat.
And then it turns around. Instead of having, this is called concave up, it turns at a point and turns concave down, and it approaches that line up there. This is a much more realistic version of population growth.